So it's time to start the Spotlight session 4, and the format is same as in the previous one. So the first presenter, Christopher, yeah, please prepare your talk. Oh, okay.
Yeah, down here. And then we're practicing that. All right, hi everyone. I'm lucky to get to meet most of you, but for those of you who don't know me yet, my name is Chris Ick. I am a PhD student at NYU's Music and Audio Research Lab. And today I'm excited to tell you guys a little bit about my work using spatial room impulse responses in the simulated realm to do sound event localization detection. So at this point, I'm sure all of you are very familiar with the task of SELD, but just as a reminder, the task here is a joint of sound event detection and localization. So to do this, obviously, we need a decent amount of data that's spatially annotated. Now, ideally, we'd get this all from the real world and use human annotators to do that, but doing so is pretty expensive, so we typically reserve those data sets for validation and testing. Because most of our solutions use deep neural networks, we obviously need an appropriate scale of data to train these models. And if we can't go out and measure all of these, the next best solution is to go out and measure a bunch of room impulse responses and convolve those with audio events to spatialize them. Now, this is a much better solution and allows us to produce a lot more data, but obviously going out and measuring these spatial room impulse responses is still pretty expensive and takes a decent amount of time. Ideally, we wouldn't be constrained by the sort of material limitations of real estate and time and effort. And because of this, simulated room impulse responses provide a pretty attractive solution to this problem. There's been a couple of work exploring this use for sound event localization detection, but there's been no direct comparisons to real-world data sets, so that's what I try to do in this work. So for this particular task at DCASE, we have a very, very nice data set provided by Tampere University, which makes use of 9 different rooms, each with a set of either circular or linear trajectories, and each one of them contains between 1,500 and 6,500 spatial room impulse responses. So my question is if we take these limitations on this real data set and apply it to a simulated data set, how close can we get to getting the same performance? So to get from this data set to actual room simulations, there's a few steps we need to take. Because the spatial annotations are provided in directions of arrival rather than an absolute position, we need to have some method of reconstructing the original geometry of the recording space, which we do via essentially distance approximation via cylindrical projection. And then beyond that, we need to know a couple of parameters about the room, like the mean absorption coefficients, and for the simulation, the number of order of reflections we're going to do. To do this, we did some pretty simple room parameter estimation using traditional signal processing methods, specifically the Schroeder method for estimating RT60. So if you look at the whole flow of actually generating this data set, this captures just about everything. So we start off with the tau SIR data set, and we have both of our multi-channel spatial room impulse responses as well as our DOAs. We pass the room impulse responses into room parameter estimation to get our mean absorption coefficients and the maximum number of reflections, and then we use geometry reconstruction to get the positions of our sources as well as the microphone information. From here, we end up with a data set that is essentially identical to the original data set, only substituting the original SRIRs with synthetic ones. So from here, we can run a couple of experiments, mainly evaluating the performance using the baseline SELD model. So we did this experiment with the original SRIRs, the simulated SRIRs, as well as a combination of the two data sets. We then evaluated these on the STARS-22 data set, which, as a reminder, is all real annotated data. And the results are what you might expect. The combined real and simulated data provides slightly improved performance in most metrics, but I think the more surprising thing is the simulated results are actually pretty close to performance, with the exception of certain metrics. So the takeaway message here is that we can use simulated SRIRs for data augmentation pretty effectively, but maybe more interestingly, the simulated ones are actually pretty close to what we get using real recorded data sets. And this is all under the constraints of a real data set. So we haven't started doing things like generating more rooms or higher density of SRIRs than before. So there's a lot of exciting things we can do with this hopefully in the near future. If you're interested in discussing this further with me, my poster's just around the corner. Here's my email address, and we're also interested in releasing this data set soon, so you too can generate your own simulated spatial room impulse response data sets. So with that, thanks.
Hello everyone, my name is Michiel Jacobs and I'm a PhD student under Professor Peter Karsmakers. And I'm here to present our work on speech obfuscation in MEL spectra that allows for centralized annotation and classification of sound events. So the problem we try to tackle is that when someone is recording a data set for sound event classification, speech signals might also be acquired, and these speech signals might also contain privacy-sensitive information, and hence we need to apply some speech obfuscation that would still allow us to let human employees label the data afterwards, and also that should still be able to have sufficiently high classification performance with deep learning models. So the methodology we applied, we investigated 3 log-MEL-based techniques for speech obfuscation that all can be applied on edge devices. The first one is in the bottom left corner, is sound shredding, where you randomly shuffle units inside of a so-called snippet, and a unit is then a block of contiguous MEL frames. Then next we tried just calculating the moving average of the MEL frames, and the third one is energy-based subsampling, which also I think speaks for itself. Then we performed 3 kinds of experiments. The first one is speech intelligibility experiments, and then we also did event intelligibility experiments with human labelers on the obfuscated sounds. And then next to that, we also performed a sound event classification on the obfuscated sounds, of course, using a deep learning model. So the results and the conclusion, the stationary sound events, there the moving average and sound shredding work best. And opposed to that, if we go to the impulsive sound events, energy-based subsampling appears to work best. If we look at the table at the bottom, then we can see different kinds of scores. The first one, the mean opinion score, this one ranges from 1 to 3, with the lower the better. And this was used in the event intelligibility experiment, in the speech intelligibility experiment. Next to that, we have the mean score, which was used for the humans to label the events. The higher the better, and it ranges from 0 to 1. And then next to that, we have the macro-Avane score of the deep learning-based models. So we can see that moving average heavy does a very good job at obfuscating. Shred heavy does a less good job in obfuscating. And then energy medium also does an adequate level of obfuscation. If you would have any further questions or interest, please come by the poster. And thanks for your attention.
Okay, good afternoon, everyone. I'm James Afolaranmi, a master's student in Tampere University, and I'm here to present my work on sound event classification with object-based labels. Yeah, so we all know that we have so many audiovisual data sets, but with like very little annotations for the audio correspondent, and annotating this data is quite expensive. So the proposal for this work is to use pre-trained models, specifically YOLO, to detect labels from the video and then label the audio clips. So for this work, we used 3 different data sets: audio set, MAVD, and Tau Urban Acoustics in 2019, and we focused on 4 main classes, specifically the classes that are most common in the traffic scenes. And also below you can see the class distribution. Yeah, it's quite imbalanced. Yeah, and also for the tau data sets, we didn't have like reference labels, so we only have labels we got from YOLO. So for the experiment, we used the baseline of OpenL3 embeddings and 3 dense layers, and then we performed like sound event classification using the model. And then we carried out the experiment on the reference label and the object-based label, and then compared them. We can see from the audio set that the model trained with like the object-based label outperformed the one trained with the reference label. And also in math, we had quite good performance. And then for tau, since we didn't have any reference label, we only have results from the object-based. So yeah, the conclusion from this experiment is that we can see that this approach is feasible and can work, and it works well for audio sources that have visual correspondence in the video. So audio sources that we can actually see their visual correspondent. And the future of this work is to extend it to other classes and other data sets. Yeah, thank you. Yeah, come to the poster.
So how do you go in from?
Control L.
Okay, yeah, right. Okay, hi everyone. My name is Janek Ebbers, and I present our paper, Post-Processing Independent Evaluation of Sound Event Detection Systems. And this is joint work with Reinhold Haeb-Umbach and Romain Serizel. So sound event detection, as most of you may know, aims to recognize all the events in an input audio and provide the sound class, the event onset and the event offset. And usually the system itself provides like soft activity scores in subsegments of the input clip, for example at the STFT frame level. So this like these soft scores, and at inference time you would then, to get a decision, you would apply a thresholding to get binary decisions at frame level, and then also post-processing to suppress like short, for example, to suppress short occurrences of the events. And then you would end up with your final detection. And actually the thresholding and the post-processing is quite crucial at the end to get a good performance. When it comes to evaluation, however, the first thing to note is there's actually a high variation in the applications. So some applications might require high recall and others may require high precision. So there's not really the one operating point we want to evaluate the systems in. So the evaluation matrix should actually capture all the different operating modes that are possible. And when it comes to system comparison, as in a challenge, for example, there's also the problem that the comparison might be a bit biased due to the thresholding and the post-processing. So if different systems use different post-processing, this can have quite a big influence on the performance at the end. And we might not notice that there's one system with a bad post-processing, which is actually very good. So it would be nice to have something to just evaluate the system itself. And so far we use threshold independent evaluation with the polyphonic sound detection score, which is basically an area under curve and therefore aggregates performance over various decision thresholds. However, this metric is still sensitive to the post-processing, as you can see here. So this is a speech detection walk curves for two different median filters. One with 0.1 seconds length and the other with 1 second length. And yeah, the difference is quite significant, and also it's worth noting that they're in different operating modes. There are different optimal post-processings, right? So here the orange one is better, and in this area the blue one is better. So in this paper, we propose post-processing independent PSDS, which follows the same theoretical derivation as the PSDS, but instead of only using the threshold as an operating parameter, we use a tuple of the post-processing type and the threshold. And at the end, it turns out that it's choosing the best post-processing for each operating mode. And yeah, we have source code available for that. And when we applied it to the evaluation of this year's Task 4A submissions, we found that actually the different post-processing in the systems do bias the system comparison, and that operating mode specific post-processing is better than a single universal one, which is also what the previous figures suggested. And the proposed post-processing independent PSDS, however, it still accounts for a performance gain due to post-processing, but in a standardized way. And it is also less susceptible to post-processing bias, which means you cannot really boost your performance by performing some additional post-processing on the system output. So if you're interested in that, please visit our poster, and yeah, thanks. See you there.
Hello, everyone. My name is Sara Barahona. I'm a PhD student from Universidad Autónoma de Madrid. And today I'm going to present you our work on multi-resolution conformer for sound event detection, analysis, and optimization. So our goal with this work was analyzing the benefits of the conformer architecture for sound event detection. And this is part of our submission to Task 4A. This task is evaluated with the polyphonic sound detection score that can be tuned to highlight different characteristics of a sound event detection. So for this purpose, two scenarios are defined. So while the first one is focused on a fast reaction upon an event detection, the second one goal is to avoid confusion between classes. So from our previous studies, we saw that the conformer architecture excels in sound event recognition, but it lacks temporal precision. So that's why we decided to employ this architecture for optimizing the second scenario of the PSDS. So for doing this and maximize the conformer's capacity to accurately identify sound event categories, we were based on the conformer winning system of 2020, and we performed first a hyperparameter tuning towards PSDS2, and then we employed different methods that were crucial for enhancing results, such as a frequency dynamic convolutional neural network feature extractor, and also including filter augment for data augmentation. And then we employed our multi-resolution approach for the analysis. So first, we wanted to analyze the system's performance across different time frequency resolution settings and compare this in this setup with the convolutional recurrent neural networks. And then this also approach was we could use it for enhancing the results with multi-resolution systems that are obtained by combining, by frame-wise averaging single resolution scores. So as key findings, well, we saw that the conformer architecture in terms of PSDS2 outperformed convolutional recurrent neural networks, but also this main limitation of the conformer system, that is the lack of temporal precision, can be solved enhancing the resolution in time. But also, when performing these multi-resolution systems, we saw that each PSDS scenario can be benefit from different time frequency resolution points. So, for example, PSDS1 is enhanced when combining resolutions that are enhanced in time, while PSDS2 benefits from combining all the resolutions defined for the conformer system. And well, if you want to see more details about this work, you can come to poster 7. Thank you.
Hi everyone, my name is Etienne Labbé. I'm a PhD student in the Computer Science Institute of Toulouse in France. I'm going to present today our work done with Thomas Pellegrini and Julien Pinquet, which is entitled Killing Two Birds with One Stone, Can an Audio Captioning System Also Perform Audio-Text Retrieval? So first of all, I will describe the task that I want to tackle in this study. The first one is automated audio captioning and aims to build a system that will automatically describe audio content using a sentence written in natural language. This corresponds to the task 6A of DCASE. And usually people employ encoder-decoder architecture with an encoder that will produce features that will be given to the decoder part that will generate the sentence for this task. The second task is text-to-audio retrieval, or also called language-based audio retrieval. This corresponds to the task 6B of DCASE, and it aims to retrieve an audio file from its database by ranking each audio file in this database using a query expressed in natural language. System architecture typically employ two encoders for this task, one dedicated to the audio file and the other one for the text part. And the two output representation will be compared using distance or similarity function. The third task is audio-to-text retrieval, and the opposite of the text-to-audio retrieval task. It is quite similar because it aims to retrieve a text from its database using an input audio file. And typically, the system that can perform the text-to-audio retrieval task can also perform this task, since we only need to put a score for each audio and text pair. So in our study, we are actually studying all of these three tasks, and all of these three tasks are multiple data that fuse audio and text information. There are even train and test on the same datasets. However, captioning tasks require to generate a sentence, while a retrieval task requires to put a score for each audio and text pair. So in our study, we propose a simple method to actually use a captioning system to perform the two other retrieval tasks. And in order to understand this strategy, we only need to see how the captioning systems are trained. Captioning systems are like language models. They will produce a sentence accordingly to the previous word in the sentence. So they will output the distribution probabilities for each next word in the sentence that will be compared with the reference one. And all of this comparison will give some cross-entropy that will be averaged for each sentence. To score each audio and text pair, we simply reuse this training setup for inference, so we are no additional training this system. And this simple strategy for using a captioning system can actually perform retrieval. It can even reach state-of-the-art score when compared to purely retrieval systems from some metrics and datasets, despite not having been trained with any negative pair or a contrastive loss. However, we found that captioning system can sometimes overestimate some caption, so a post-processing strategy is required for the audio-to-text retrieval task, but not the text-to-audio task. And finally, we also extended our study by testing the ability of our model to discriminate the sound event relation, like superposition or sequence. Thank you very much for your attention, and please visit our poster if you want to see more details.
Okay, hello everyone. My name is. Oh, I'm sorry. Oh. So hello everyone. My name is Vuegen Liu. I'm a master student from Waseda University, and the title for my presentation is a mask modeling dual vision transformer with multi-layer feature fusion on respiratory sound classification. And so the main task in this research is the respiratory sound classification. The task is to identify the potential diseases from the recorded respiratory sounds. As you can, oh, it's automatically. plate. I'm so sorry for it. As you can see, different kinds of the bird sounds that can indicate different kind of potential diseases. And the dataset we use here is the ICBSI respiratory sound database. And it consists of the sounds that's collected by some microphones or the stethoscopes from different locations of the patient's chest. I'm going to just pick up some samples. Oh. So this is sounds for some airway conditions. Oh. And this is for some cardiorespiratory conditions. And the combination of these both anomalies and just the normal ones. So the performance of the features from the pre-trained vision transformer can be imbalanced due to the structure and the training metrics. So the main strategy we used here is to fuse various layer features from the vision transformer encoded from the SSL learning framework. And we also introduce a kind of learnable layer-wise ways to balance the informations from the layers. Oh, I see. Oh, okay, that's fine. So, and then it's come to some key findings in this work. It's proved that our strategy of the fusion that can improve the performance on this kind of task. And in our analysis of the layer-wise ways, we find that the later layers they can contribute more in the fusion. Anyway, sorry for such a terrible presentation. And if you're interested, please just check the posters. And thank you very much.
So, yeah, hi everyone. I'm Modan Tayer. I'm a first-year PhD student under the supervision of Mathieu Lagrange, and I'm gonna introduce you our paper, which is spectral transcoder using pre-trained sound classifiers on undersampled spectral representations. But first, let's see a little bit of context. Let me introduce you to noise maps. So, what is a noise map? A noise map represents a level of noise, usually at the scale of a city. And here on your left, you can see like the noise map of the city of Lorient. The more red it is, the more noise there is in the city. It is used by city stakeholders to make decisions regarding the city and the noise of the city, and to better understand how the sound works in their own city. The only thing is, like a noise map only represents level of noise, and so we all know that 80 decibels of birds doesn't mean the same thing as 80 decibels of traffic. And so what we'd like to do is go from those kind of noise level representations to sound source presence representation, where we could represent the presence of, for example, birds in the city of Lorient. So here on your right, here is a map. The more green it is, the more birds there is in the city. And so what we'd like to do is do those kind of maps on your right. And what we have access to is a data set, which is called Lorient Sense Audio. It's actually 3 years of audio data recorded with 75 sensors. We were recorded simultaneously in the city. And the thing is, with these data sets, we'd like to do maps, but we don't have access to audio. We only have access to fast third octave spectrograms, which can be seen as really rough audio data, really degraded audio. But it has the advantages of being extremely light, so easy to store, and to respect privacy because it makes speech unintelligible. And so with that, we'd like to make some sound source classification. And lucky us, we have access to pre-trained classifiers for sound source detections, which are called PANs. So what they do is they take a waveform as input, they transform it into MEL spectrograms, and then they are able to detect the presence of different kinds of sound sources. But us, we don't have access neither to raw audio or to MEL spectrograms. What we have are fast third octave spectrograms. So our idea was to transcode fast third octave spectrograms into MEL spectrograms in order to not have to train another model. So we call that a spectral transcoder. And so we trained it with an innovative teacher-student approach, which leverage the outputs of PAN to learn how to do a super resolution, because ultimately, like fast third octave spectrograms is lower quality than MEL spectrogram. And we found that like this method, this teacher-student method, outperforms state-of-the-art teacher-student methods. Obviously, like those results are really vague and catchy. So please come and see us at the poster session if you want to know more about our results. Thank you very much.
Okay, hi everyone. Starting now, I talk about summarization of the event classification with class-propagated unit using large-scale pre-trained model for optical fiber sensing. I'm a presenter, Noriki Tonami from NEC Corporation. So this is a research question. It's really simple. So how do we utilize pre-trained audio recognition models for sound-aware optical fiber sensing? Maybe optical fiber sensing is a new topic in the DCASE community, including also the synchronous process-related community. So maybe nobody knows optical fiber sensing. Anyone knows it? Please raise your hand. Oh, all right. Thank you. Anyway, so we focus on sound-aware optical fiber sensing. This is very simple. By using optical fibers, sounds or vibrations or temperature can be captured. This optical fiber is really normal, simple fiber. So here we have two problems, optical fiber sensing. First, sensitivity of the fiber sensor. So the data is really noisy and distorted compared with the microphone data. And the amount of the open source data is really limited. So in other words, very small amounts. So here, how do we use audio models as a research question? This is the proposed method. So as previously mentioned, we have two main problems. First, to address noisy and distorted data, we employ knowledge of large-scale audio recognition models and human knowledge. Human knowledge imparts the classification performance. And to address the small amount of training data, we train event recognition model without target domain data. So here, target domain data means optical fiber sensing data. So in the training stage, so we train the audio recognition model such as PANS model with microphone data as an input. And the inference stage, so the input data is microphone data is switched to fiber optic data. And moreover, we also utilize human knowledge. Human knowledge is, I think, in general, so it's more powerful compared with the such as statistical knowledge. So in specifically, we added the cross-level probability in the intermediate layer of the DNN. So this is kind of also regarded as, so in this work, so spectral subtraction in intermediate layer of the DNN. So note that here we focus on the task with event classification. So finally, this is a main outcome. The proposed method improved the accuracy of 13 percentage points for event classification using ESC50 dataset on the condition of noisy and really distorted. This is kind of optical fiber sensing situation. And we also introduced the simulation of the optical fiber sensing. So this is to mitigate the lack of the fiber optic data. So as for the application in the future work, so optical fiber sensor has a big potential, such as huge area sensing over 100 kilometers. That's it. Thank you.
Good afternoon, everyone. I'm Snehit, and I'm here to present you with my work. It's a synthesis dataset that we have created, and we named it as TELIN-US. We called it like Spatio-Temporally Linked Neighborhood Urban Sound Database. So, giving you the motivation, I will like you to introduce you with the introduction. We believe that within a connected neighborhood, the sounds that we hear is depend on where we are and when we are, which means that the sound that we heard is depend upon the different location and the different times that we heard it. So we propose this idea like this kind of neighborhood-based data generation can open up the novel opportunities for using it into the user-centric applications. With these great researchers and the great research in this field of acoustic and audio domain, we have this huge variety of data set. Each of them is designed to tackle a certain set of problems. And but by far, we believe that most, if not all, haven't think about this kind of a data set which should be representing a connected neighborhood data set, and which is spatio-temporally varying in nature. So, however, the team of Sonic has built one such kind of a data set which also equipped with the spatio-temporal metadata, but their primary focus was on the noise events. And taking the lesson from them that it took a long time to collect such data as recording, and to get it annotated is also a time-consuming task. So we propose this idea of having a synthesis data could be a more feasible one and practical one. So we propose this methodology, and it's different than the machine learning technique because we are here merging the different kind of sounds which all together in a pattern that should represent a real-world scenario. So we first propose these preconditions that we propose this map for this data set. And we propose that specific sound locations for the microphone that you can see in the map, and those are the sound classes variation within the microphone that you can see. And to create that, we select scene-specific sound classes that we choose from the previously published data sets, and we follow the real-world surrounding sound variation patterns. On top of that, we go for traffic synthesis, which is representing the connected neighborhood environment. And then at the end, we go for scene synthesis, which is basically synthesizing a particular scenario at one microphone location, where we consider the distance scaling first, which is representing how far the sound source is from the microphone location is. And second is the dense scale, which is representing how much rush hour the particular scenario is in. And doing so altogether, we merge the different sound classes, audio segment on top of each other, and then we just get the audio clip, which is representing a scenario. Doing so, we get the data set with these audio files, and we also provided the metadata as well, which is also having the strong annotations for the sound events and the spatiotemporal metadata. Coming to the analysis, we did perform a listening test for this, where we choose 3 different annotators out of 6, and we asked them 2 questions. Did you feel this? Did you feel this sound to be heard like in rush hour, or how natural the sound feels like? And these are the results that we get. But this was just about the brief of my work, and I would like you to invite to my poster. Please come and join me to get more of it. Thank you very much. By the way, this is my lab's QR code. If you want to get more about the research in my lab, please. Thank you.
So that's all the Spotlight presentation. And unfortunately, we don't have coffee break in this time slot. So let's move on to the next room and continue discussions. Thank you.